So let us continue. A disc-shaped part is cast out of aluminum. The diameter of the disc is 650 millimeters and its thickness is 16 millimeter. If the mold constant is 2.2 seconds per millimeter square in Sharabinov's rule, how long will it take the casting to solidify? So let us go back to the formula. Okay, if you remember, the solidification time can be calculated as T total solidification equal to the mold constant times V over A squared. Now, V is the total volume and A is the lateral area. So now, just I should pay attention for units, okay? So here, since the mold constant is given in second per millimeter square, so the dimensions should be in millimeter. Here they are already in millimeter, so I don't have to do any conversion. Now, just I should find V and A. So I should know the geometry of my cast. I have a disc-shaped part. So for a disc, okay, I have that the volume is, of course, pi d square over 4 times the height. So I know the diameter and I know the thickness. So I can say that the volume V is equal to pi d square over 4 times the thickness or the height if you want. So H, okay. I just have to replace D by 650 millimeters and H by 16 millimeter. I get the volume value. Now what about the area? How to calculate the lateral area here? So first I should consider the circular base, up the top one and the bottom one. So I have 2 times this area, okay, plus what? Plus this area here, the lateral area here. How to calculate this part? What should I do? The area of this part. It is
2
in
pi r times the height.
exactly. I get the perimeter of the base and I multiply by the thickness. So the total lateral area is 2 times the base area, which is 2 pi d square over 4 or r square if you want. Okay, plus for this lateral conference, so I have 2 pi r times thickness times h. In this way, I can get the value of my total lateral area, and then I numerically replace in my formula. And since my dimensions are in millimeter and my mold constant in second per millimeter square, I will end up with the time in seconds. And I can convert it depending on the question to minutes or hour. Okay. I'll always try to verify your answer. If you should get a logical result. So here, for example, if you look at numbers, so first I got the volume, pi d squared times thickness over 4. For the area, it's 2 times base area plus pi dt. I get V and A. I replace into the Sharabinov's rule. I get a time that is physical. My volume is not very large, so I don't expect to have 1 hour of solidification, for example. Okay, so always check your answer to see if it's reasonable or not. So I have here 127.9 seconds, which correspond to nearly 2.13 minutes. Any question on this problem? Yes, Naaman, concerning the area, look, even if it's not a closed mold, you have that, even if it's, if you consider an open mold, also you have the area of interaction with the ambient. It's right that in general, this formula, Sharabinov's rule, is considered for closed molds in general. But if they don't specify anything, so you can use the same rule. Okay. Anyways, the disk you can cast it with a closed mold or an open mold. For an open mold, maybe the formula will be different because you will have one phase interacting with the ambient conditions. So this will complicate a little bit heat transfer. But since they didn't mention anything, so you can consider it's a closed mold and perform your calculation. Okay. Another problem, the total solidification times of three casting geometries are to be compared. The first is a sphere with diameter of 10 centimeter. The second is a cylinder of diameter and length both equal to 10 centimeters, and a cube with each side equal to 10 centimeters. The same casting alloy is used in all three cases. The first question is to determine the relative solidification times for each geometry. Then, based on the results of part A, which geometric element would make the best riser? And finally, if the mold constant is 3.5 minutes per centimeter square in Shrobinov's rule, compute the total solidification time for each cast. So always, when you want to compare risers, first you compare the solidification time. So this is a general procedure. If you have different solidification times, then you select the, which one? The highest or lowest solidification time? Exactly, the highest, because we want to have the riser solidifying after the main cavity. Okay, so this is the first criteria. Now, in case you got same solidification time for the three shapes, then what will be the criteria of selection? So if all will have same solidification time, then I will compare what? I should try.
Volume?
Yes, volume. I will select the lowest volume or the highest volume.
Highest.
No. Why no? Because I want to reduce the waste. Okay, so in general, I will not need a very large amount to compensate for shrinkage effect and for voids. So I should minimize the volume as much as possible to not have, because after when you have the final cast, you will trim, you will cut your riser. Okay, so in order to reduce the waste metal, of course you can use it again by remelting, but in order to not lose heat, if you want, it's better to reduce the volume as much as possible. So this is the criteria for riser selection. First, compare solidification time. If I get different solidification time, I select the highest one. And if I get equal solidification times, then I compare the volumes and I select the smallest volume to reduce weight. Okay, so let us see here what we will do. First, they told us that we have the same casting alloy in three cases. Plus, they should add in the given to be more accurate. Plus, same metal, same mold metal, and same pouring temperature. So I will add here plus same mold metal, and because this will affect what? Will affect the mold constant. So if I have same mold constant, in order to compare the solidification time, it's enough to compare V over A. The one having highest V over A will have the highest solidification time. Okay? So let us start with the sphere. For a sphere, the formula for volume is pi d cube over 6. Okay? So you can get what is the volume. Here they gave the unit in centimeter, 10 centimeters. They choose to switch to decimeter because maybe it's simple for calculation. It's 1 decimeter. So you can do what you want with units. So, but you should get V and A in same units. If you use decimeter and volume, of course you will use decimeter and area. Now, for the lateral surface area of the sphere, it's pi d squared, okay, or 4 pi r squared. So it's pi times 1 square. We get in this way V and A. And when you have the ratio V over A, you can get that this ratio will be in unit length. So it's 0.1667 decimeters. So you can deduce that the solidification time, okay, is 0.02778 times the mold constant. And since you used your value of V over A in decimeter, then you should make sure that the mold constant is in second per decimeter square to get in total the solidification time in seconds. Now we move to the cylinder volume. So for the cylinder, we should calculate volume also and area. So for the cylinder, we did now in the previous problem, it's a disc, so it's similar to cylinder. Just here, maybe the thickness is for a cylinder. You can consider that you have a higher thickness. So for the cylinder, same method to calculate the volume. It's pi d square over 4 times the height. And to calculate the total lateral area, you have to take 2 times the base area times this peripheral area, which is 2 pi r times the thickness. So you can see here that we did 2 pi d square over 4 plus pi dl. Okay. In this way, once you calculate V and A, you can find the ratio, and we will see that we will obtain similar solidification time. So until here, these two are similar in total solidification time. But if you want to select between them, we will choose the lower volume, which is the volume of the sphere. So until now, I will select the sphere. Now, the third option is the cube. The cube for each side 10 centimeters or 1 decimeter. You know that for a cube, I have 6 faces. Okay, so the lateral area will be, the total area is 6 times the face area, and the volume is the side cube. So V equal to L cube, 1 to the power 3. And the lateral area is 6 times the face area, because if you draw the cube, well, it's not a cube here, but if you draw it, you have 6 faces, okay? Up and down, right and left, okay? So you have in total 6, and it's 6L squared. Now, if you do V over A, you get also the same ratio of the previous ones. So for solidification times, they are comparable. So if you just take the criteria of solidification time, they are equivalent. But it's not, once they are equivalent in solidification time, you will not stop here. You will say, I will search for the lowest volume. And among the three, you have the sphere having the lowest volume. So I will select as my riser the sphere. Okay. So here you can see again these details. So first, we have all 3 shapes are equivalent. We will not say, if you want to be more accurate, not as risers, and as solidification times. They have the same solidification time. Okay, since they have the same solidification time, I will take another criteria to compare. So here, accordingly, we will reserve the lowest, okay, volume, which is the volume of the sphere. So here we will select the sphere as riser. Now concerning, just for calculation, they gave us the mold constant. If you want to calculate the solidification time, we should make sure to use good units. Since V over A is expressed in decimeter cube, then we should convert here from minute per centimeter square to minute per decimeter cube. So you know that 1 centimeter, okay, correspond to 0.1 decimeter. And since you are dividing by decimeter square, so you should multiply 3.5 by 100, okay? So 3.5 minutes per centimeter square is 350 minutes per decimeter square. And then the solidification time is around 10 minutes, okay? Any question on this problem? Do you have a class now? We just need maybe less than 10 minutes for the remaining problem. Or if you want, or if you prefer, we continue next time as you like. So what do you prefer?
Doctor, I have class at 11.
Okay, so we continue. It's just still one problem. We continue it next Wednesday. We continue
إذا problem صغير بنعمله إذا بيخلص.
هلا هو كتير صغير يعني 5 minutes يمكن.
أنا ما عندي مشكلة إذا بنعمله.
Okay, yeah, let's do it. In aluminum copper alloy, 92% in aluminum and 8% in copper casting is made in a sand mold using a sand core that weighs 15 kilograms. Determine the buoyancy force in Newton tending to lift the core during pouring. Given that the sand density is 1.6 gram per centimeter cube and aluminum copper density is 2.8 gram per centimeter cube. For all you should know about buoyancy is that if I have, you know that in general the core, when after pouring, will be immersed in the fluid. Okay, so when you have a solid immersed in a fluid, what will happen is that the fluid will exert on it an upward force, which is called the buoyancy force. Okay, and in general, to know the total resultant on the core, we should compare the buoyancy force to the weight. Okay, so you have the weight is downward and the buoyancy force is upward. So in case they are equal, then we will have a net action of 0 on the core, so it will not experience a lift. But if the buoyancy is higher than the weight force, then we will have a total lift force upward. While if you have the weight higher than the buoyancy, then you have a lift downward. So in general, in order to avoid lift effects, we add chaplets to the core. You have seen chaplets in the course material. Okay, you should have, and you will see in a problem in the homework. So I posted the homework for you on this chapters 7 and 8. Please try to do it. We will correct it together after as review for the exam. So you have chaplets at downward to oppose the weight before pouring, because you know before pouring you only have the action of the weight. After pouring, due to buoyancy effect and in general the density of the fluid is higher than the density of the core, which will cause a total lift force upward. So we should put chaplets on the upper side to oppose this. Okay, now how to calculate these forces? For the weight, it's very simple. The weight is the mass times g, so no problem with it. Now for the buoyancy force is calculated as following. It is equal to rho of the fluid, so here rho of the metal, molten metal, okay, just after pouring of course, times the volume, what we call displaced volume. Displaced volume. What is displaced volume? When you put your core into the fluid, it will take a place, it will take a certain volume from the fluid. And this is called the volume displaced, okay? This is the volume occupied by the solid. It will take a certain place from the fluid, okay? Now, in case you have your core is completely immersed, which is in general the case, okay? When your core is completely immersed in the fluid, then what will be the volume displaced? It will be equal to the volume of the core, okay? So here you multiply by the displaced volume of the fluid. So here, because since my core is completely immersed, then I can say that just guys, I should add to rho times V, I should add G, because you know rho times V will give you a mass to multiply by G to get the force. So if you want here, the buoyancy force, FB, is equal to rho of the molten metal times, because V displaced is equal to V core, which is completely immersed in the fluid, times G. Okay, so now to have the net lift force, all we have to do is to say that F lift is equal to buoyancy force minus, in general here they confuse terms, يعني they call the buoyancy force هي الليفت. خلينا نعمل فرق بيناتهم. Okay, الbuoyancy هي the upward force of the fluid on the core. And I will be clear in the exam. I will tell you the lift force acting on the core, let's say. If I just ask for the buoyancy force, you just do this term. Lift force, here difference between them, FB minus weight. So here, if I replace each term by its expression, the buoyancy force here, rho, molten metal, times V of the core, times G, while weight is minus M times mass, of course, mg. Okay, what is m? It's rho times v, but which rho? Now I want the mass of the core, so I multiply by rho of the core times volume of the core. This will give me, this is the mass of the core, and here it's already directly given, times G. So I have, if I take into factor V core times G, I will obtain V core times G, which is what? Which is the mass of the core, okay, times rho of the molten metal minus rho of the core. And in general, the core density is lower than the density of the molten metal. This is why I get a total lift force upward, okay? So that's it. If you look at the solution, just, it's very simple. First, I calculate, I have the density, okay? Just pay attention for units, okay? So in case I want my total force in Newton at the end, then my density should be, I should have kilogram per centimeter cube, because the volume is in centimeter cube. So when I multiply rho by V, V should be in centimeter cube to get the mass in kilogram. And the force is mass times G, okay? So as you can see here, I can get the core volume by dividing the mass by the density, okay, the density of the sand, because the core is formed from sand. And once I have this volume, I can apply the formula for buoyancy force, or lift force if you want, which is the upward buoyancy minus the weight force. So in total, it's G times, if you want, the variation in mass, okay? So it's mass of the displaced metal minus mass of the core. So I get the total lift force in Newton, okay? Any question on this?
Doctor, هيدا الكويستشن related ل part 2 of chapter
ايه
8.
هيدي ريليتد، بعتقد المفروض تكون مرقه ببارت 1 اذا ماني غلطانه، if not بعد بتكون ببارت 2.
Okay.
بس هي من اول البروبلم، so I think it should be in part 1. I don't know. Anyway, يعني حتشوفوها يعني I will give you time يعني on Wednesday I will not have class, so you finalize chapter 8 with all videos, so that on Friday we can start a new chapter.
Okay.
Okay. Any other question?
Doctor, the volume of displaced fluid عقيلة بناخده the volume of the core.
لا حسب، يعني حأعطيك example. لو كان ال core like this, so إذا ما كان completely immersed, example يعني مثلا let's say الميتال وصل لهون، molting metal، ساعتها شو بيكون ال displaced volume؟ بيكون بس هيدي البارت، يعني you will just take the part of the core inside the molten metal. كل شيء outside ما بتحسبي بالvolume displaced.
Okay. Okay, thank you.
Any other question on this?
Thank you, doctor.
Welcome,
Bye.
guys. Yalla, see you next time. Bye.